Chapter 4, we're going to be talking about polynomial and rational functions. We're not necessarily skipping Chapter 3, we just finished Chapter 2, but Chapter 3 is contained, the information that we're going to be covering from Chapter 3 will be contained in Chapter 4. So nothing to be concerned about, but nevertheless, here we are in Chapter 4. We're going to be talking today about Section 4.1, Polynomial Functions and Models, and then the next lesson will cover 4.2. We may or may not cover 4.3. That's kind of a question mark right now. But then after that, though, we will cover for sure sections 4.4, 5, and 6, where 4.4 and 4.5 we're going to be talking specifically about rational functions, and at the very end of the chapter we're going to put them both together. Okay, and so let's go ahead and get started. I'm going to go through these slides pretty quickly, so if you wanted to write something down, just pause the video as soon as you see something that you want to write down. Section 4.1, we're going to be identifying, the first part of this, identifying polynomial functions and their degree. So just to give you a heads up on the kind of like the formal definition of a polynomial function, I don't necessarily like to explain polynomial functions using that formal definition. I would rather use a definition like this, where polynomial functions are, let me use a different color, are functions in which f of x is equal to some constant a times some x raised to some power plus b multiplied by the x raised to the some power minus 1 plus so forth. So you have a bunch of terms, maybe just one, maybe more than one, but you have to have at least one term. And then at the very end you've got some constant down here, and then that's that a, where a, b, and c, and then any other terms in there would have coefficients that are real numbers. So the coefficients, so here's the deal. You can look at an equation, and as long as the coefficients are real and the, let's use a different color, and the exponents are whole. There's got to be some sort of a rhyme or a song or something you can make out of that. Coefficients must be real, exponents must be whole, and what do I mean by whole? I mean like whole numbers. And just to make sure that we're all on the same page here, whole numbers are the numbers that start with 0 and then you just increase by 1. Okay, so those are all the whole numbers. 0, 1, 2, 3, 4, 5, and all those whole numbers. Okay. And so yes, whole numbers are part of the integer family, but the integer family also contains negative whole numbers, and so we can't have, though, negative exponents if we want to, if we have a polynomial function. So that's kind of a neat thing, because we have a lot of consistency among all polynomial functions. They're nice and smooth and all that kind of stuff. So this is what I'd like you to remember here. It's hard to remember this complicated definition, but there is the definition there if you really want to take a look at it. And let's talk about the degree of a polynomial as well while we're here. The degree of a polynomial is always the highest power of all of the terms. Okay, and so let's write that down. Highest power. Let me get a good colon here. Highest power. Okay, the most powerful term gets to control or gets to identify or to name the degree of the polynomial. So let's take a look at a couple of these in our next slide. And hold on one second. So our goal here is to take a look at these 6 functions. They're all functions, and the question is, are they polynomial functions? So based on the definition, pause the video and give these a try, just to make sure you understand what is a polynomial function and what is not. And if you do identify that one of these or more are polynomials, then make sure you identify what the degree of the polynomial is as well. Okay, so pause it, because I'm going to go ahead and show the solutions. So for the first one, A, we can see that the leading term, if you just circle leading term, meaning the term with the highest degree in it, leading term here would be an x to the 8th. We can see all the exponents are whole and the coefficients are real, and so yes, we have a polynomial function and the degree is 8. Okay, 8th degree. I'll write the degree, the word degree for this one, but all the other ones I'm just going to write the number. Okay, so then on the second one we can see g of x equaling, this is a polynomial divided by a polynomial, and we never said that that was a polynomial as well, but this would be no. Okay, so no, that's not a polynomial. Part C, this might have fooled a couple of you, but if you think about the definition, do we have whole number exponents and do we have real numbered coefficients? Well, we don't even have an x, so you might have thought, well, this is not a polynomial. But x to the 0 is just a fine number. X to the 0 just represents 1, but this would be yes. Okay, and then the degree would be 1 for this one. Okay, so that might have gotten you. Don't let that get you again. For D, if we multiplied out these two terms, or I should say these two binomials, we would see that the first term is x squared, and then we have, what is that, negative x, or minus x minus 6, and so we would see, yes, that this is a polynomial function, and the degree is 2. The second degree polynomial, we call that a quadratic. Okay. Well, here for part E, you can see that we have an exponent that's not a whole number, so this has to be a no, not a polynomial. And don't let the fractions fool you. Again, the coefficients are real numbers. We know that all these fractions are real numbers, and the exponents are whole numbers, all of them. So we say yes for this guy, and the degree of this polynomial is 3. So also we want to be able to determine just by looking at the graph if the graph is of a polynomial function or not. And one thing that's consistent, like I said, about all polynomial functions is that they have a domain of all real numbers, they're nice and smooth, and so that's what we want to look for. Is the graph nice and smooth, or does the graph have sharp turns and corners and cusps and maybe gaps in it? But again, this is a yes, this is a polynomial function. And we know that because of the smoothness of the curve, and it's continuous. It doesn't have any breaks in the graph. It doesn't have any openings in it. The domain again is all real numbers. So yes, that's a polynomial. And this would be no. You could clearly see, if you understand polynomials, we have sharp points and we have a cusp here. We have an opening, a gap. That would mean the domain is not all real. Well, we can still have a gap and have a domain of all real numbers, but again, the smoothness of the curve is what we need to have a polynomial function. So another concept I want to talk about here is the concept of a power function. One of the things that we'll talk about is finding a model for a polynomial function. When we're not quite sure what the graph of the polynomial looks like, we can find a model, and that model is in the form of a power function. So one of the questions that you'll be asked is, name a power function that would be an end behavior model for this particular function. Okay. Now, just so you know, the power functions have a specific form, and the form of a power function would be some constant multiplied by x to some power, and in this case these powers must be greater than 0. So positive whole numbers for the exponents, and some a that's not equal to 0. A has to be a real number, and again the exponents have to be whole numbers, but in this case for a power function you have to have x or n being greater than 0. Okay, so you can see some examples down here of some power functions: 3x, negative 5x squared, 8x cubed, and negative 5x to the 4th. These are all power functions, and we're going to do a neat little interactive figure here which will illustrate a little bit better about what power functions do for us. So let me get that ready. Actually, what I'm going to do is I'm going to do that in the next, show that in the next video, because the last time I did this I had to do this video over. Once I got past a certain point, I lost the video. I don't know where it went. So again, next video we'll talk about, we'll show the interactive figure on these end behavior models.